So, thank the organizers and thanks to everyone who put this together. And if you might have guessed from my fairly generic title that I'm going to be talking about a lot of different things, all related to understanding and improving quantum annealing. The disadvantage of talking about many things is I can't go into a lot of depth in them, but there are plenty of references. And so here's the overall sort of idea of the talk is a broad review that basically breaks down into 3 themes, and I'm going to quickly mention a sort of fun side project at the beginning, but then sort of 3 themes. One about sort of understanding rapid quenches, understanding physics, or understanding quantum annealing outside of the adiabatic regime, particularly from the perspective of quantum walks, some projects in that direction, and then sort of trying to see what you can do there. Then talk about what I've broadly called hardware-aware encoding, basically different tricks you can use that will hopefully give you benefit from knowing that you're actually going to be using something on a real device. Because D-Wave devices are the large devices that are available. This is going to focus heavily on experiments on D-Wave devices, things like domain-long encoding. And then the last bit, I'm going to just talk about looking into what else you might do and sort of forward-looking work. Just a quick advertisement that I guess I should say now former student, has built a video game based on deep model quantum computing. It's based on a full state space visualization. There's no math or anything. It's very fun. I'm not going to talk much about it, but it's worth mentioning. So now on to the main talk. So we like to think about adiabatic quantum computing. It's a very important sort of tool people often use to think about quantum annealing and understand it. The basic idea is you map a hard optimization problem to a Hamiltonian, and you slowly change from a driver Hamiltonian with an easily prepared ground state to a problem Hamiltonian. And the adiabatic theorem of quantum mechanics guarantees that if you run long enough, your success probability is arbitrarily close to 100%. So this is fantastic. It's a nice bit of math. It has plenty of advantages. But there's also a disadvantage of doing theories based on the adiabatic theory. And that's that if we think the quantum equivalent of P not equal NP is true, which most of us probably do, that you're not going to be able to solve hard optimization problems in polynomial time on a quantum computer. Technically, this is different than P not equal NP because that doesn't include quantum computers. That's only classical computers, but the quantum version of that. If you have an algorithm that succeeds at order 1, your total runtime would need to be exponential in the size of the problem. And if you're doing a coherent algorithm, that means you need to maintain coherence that long. That's probably not ideal. And so we probably want to think about other pictures of what is going on beyond just the adiabatic picture. So what can be done if we're thinking of we have this problem that we either can't succeed with high success probability, can't succeed with high probability, or we have to, stay coherent for a very long time. There's kind of 2 options. I mean, there may be other ones, but there's 2 main options, or 2 that I'll consider here. One would be error correction to just somehow manage to maintain coherence for that long of a time. That's really hard work. I've sort of drawn a wrench here there. The other more subtle thing that could happen is what if you just succeed with a low probability? And then you can imagine if you run for a short time, your success probability is exponentially small, but you just keep running. This kind of feels like you're playing the lottery. It's, I would say, conceptually unsatisfying, but theoretically, you know, unless, you know, again, the quantum version of P equals NP, I believe that NP is contained in BQP, which most people don't believe, any method you use would always have to take exponentially long. So there's not really anything that's actually worse about doing this, or at least not obviously. So thinking about this setting where you're actually running for a short time and succeeding with a low probability is worthwhile, and establishing theory in that setting is good. Of course, there's a hardware motivation for this. We've heard about this in various D-Wave talks, that flux qubit technology has improved to the point where you can actually do rapid enough quenches that you can ignore the effects of the bath. So these are definitely very fast quenches. You can ignore the fact that it's an open quantum system if you run fast enough. And you can imagine now, okay, the idea of rapid, way too rapid for the adiabatic theorem, but still fast quench, where you don't have to think about open quantum system effects, really is realistic. That really is a realistic setting for doing theory. And we want to understand what's going on there. So this is a slide taken from a longer talk, but you can use an energy conservation argument that you can do in a single quantum walk. So a single quantum walk is you just have a driver Hamiltonian and a problem Hamiltonian turned on at the same time, and they just have fixed values. A continuous time quantum walk that obeys energy conservation. If you then imagine a trotterization, what you basically can do is you can make arguments that in each trotter stage energy is conserved. Between the stages, energy isn't conserved. But if you're always making the strength of the driver relative to the problem Hamiltonian smaller, that actually takes energy out of the system. So you have energy conserving stages, energy removing stages, and both of those mean that your average energy will go down. And if you take the limit, you can make a very general result about rapid quenches. So if you have monotonic rapid quenches where this ratio is always decreasing or staying the same, and you start in the ground state of your driver Hamiltonian, and then there's a technical concern about the driver not being a gapless, that doesn't matter for real problems. You can make an argument that you're always actually doing a bit better on average than if you random guessed, if you did a random guess. And the advantage here is, unlike the adiabatic theorem, I haven't referenced how fast any of this happens. Discontinuities are okay. I haven't said anything changes continuously. And I haven't actually said that the driver Hamiltonian is diagonal on an orthogonal basis to the problem Hamiltonian. Starting states can be biased. I won't talk about this in this presentation, but that is important implications for hybrid algorithms. And the paper talks more about why that's important, the one that's referenced on the bottom there. So what I'm going to talk about here, after giving that sort of introduction to some of the ideas we've been thinking about, is this general idea we're trying to reduce energy. How else might you reduce energy in a quantum system? And we have this rapid quench picture. That's almost, in a way, you're using the fluctuations against the driver as a system sort of own bath. What happens if you add an external spin bath? Basically, what if you remove energy by coupling to a spin chain, uncoupling, and doing this repeatedly? There's many details in this paper that I don't have time to go through, but this is the basic concept of this sort of collisional cooling scheme. If you do this, you can plot the expectation of the Hamiltonian or success probability, and you can see, success probability goes up, and energy goes down. You can see things kind of plateau. You could perhaps say, well, what's happening there is when I couple, I'm introducing energy to the system. If I just start coupling weaker and weaker, maybe I can avoid that. Maybe I can avoid hitting a plateau. Although there you're going to be able to take less and less energy out. So there's kind of a trade-off, I would say, in this setting. And if you keep everything fixed, you reach an equilibrium where basically no more energy can be extracted. In the paper, we actually did this the other way too, where we started in the solution and started doing this coupling state, and we see it reaches the same equilibrium as if you go from equal superposition. So it really does kind of reach an equilibrium. There's a lot that I won't cover here, and I encourage you to look at the paper if you're interested. So there's disadvantages to the setting. Then the coupling introduces energy back into the system. Each collision only removes a small amount. So if you want to improve some of these ideas by building a protocol where you're using extra bits to remove energy from the system, to actively extract energy and entropy, what you can think about is something where you're not just coupling a bath with a fixed Hamiltonian, but where you're actually annealing a part of the system that's acting as an artificial bath. And this also deals with, leads to a subtle way to deal with the coupling induced energy. So you can imagine an energy extraction protocol. Basically what you do is you couple a system of single spins that are initially in eigenstates of in the ground state of a transverse field Hamiltonian, and then you anneal that field down. You still have some energy that gains that you add when you couple, but if you have the same number of spins in your system, in the system you couple, as you do in the actual system you're taking energy out of, you can argue that in the adiabatic limit, instead of taking just a small amount of energy, no matter how you do it, you can actually, if you started the bath in its ground state, whatever the system is in, to start out with, even if it's in a mixed state, you'll always be, you'll always obtain the solution, and then you'll obtain some garbage on the bits you don't care about, but they're bits you don't care about, so it doesn't matter that they're in some garbage state. The way to see this sort of mathematically is you'll have a 2 to the n fold degenerate ground state where the system is in its ground state and the bath is whatever, and there's details on how this protocol works. You have to decouple in a certain way. This scales quadratically so that perturbatively that coupling is weaker than your Hamiltonian accelerated bath system. But if you do it right, it works. You can demonstrate this numerically. Of course, the motivation I gave at the beginning, what's really interesting, at least for us, isn't actually the adiabatic limit. It's doing things much faster. And this is where I actually don't have much more to say, because unfortunately my collaborator was working on this with institutions. And so this has been a little bit slower than we'd hoped, but we are working on this. I'm just going to say, watch this space. And you can almost apply this energy redistribution picture. The only place you're introducing energy back into the system is when you couple the bath to the system. So when you turn on this term here, which couples the system to the bath. You have the bath of the transverse field, you have coupling between the system and bath, you have the driver Hamiltonian problem. But this, when you turn that term on right there, that's when you can introduce energy into the system. But yeah. So this is an interesting area to watch the space in, but I don't have too many more results to show beyond what I showed in AQC. Another bit of work we've done kind of in a similar direction is thinking of continuous time versus sort of digitized, what I call digitized continuous time. So this is thinking of if you do a continuous time quantum walk where you leave everything fixed, but you have the driver and the problem Hamiltonian simultaneously on. This is much more what you have in an analog setting, versus what you do in a QAOA type algorithm, where you have the problem, and then you have the driver and you turn it on, and perhaps you do that multiple times. You can make general arguments that if you make your steps small enough, these two reach the same limit, they behave the same way, but we're going to think outside of that limit, which is what you do practically on a gate model machine if you're doing the QAOA thing. And we're going to look at this from perspective of comparing not an anneal with a quantum walk, where an anneal you're continuously changing the Hamiltonian, or sorry, not an anneal with a QAOA type protocol, but a quantum walk with a QAOA type protocol. So where you're leaving the terms fixed. Part of the reason we do this is that you kind of have the same number of parameters. We know from the energy conservation arguments, being able to sweep the Hamiltonian is actually a powerful way to pull energy out. So you can kind of say, well, you're giving the analog approach a big advantage if you allow it to do that. What happens if you don't do that and give it that advantage? Do you still come out ahead? And we have this paper that I wrote with Viv and others. And our answer, if we look at a single stage, so this is a single stage of quantum walk, meaning problem and driver turned on at the same time, starting a uniform superposition of all the states, and just run it for some time, versus QAOA, where you do problem, then you turn the driver on, and you don't have them on simultaneously. 100 random 10 variable spin classes, both in terms of energy and in terms of success probability, numerical simulations, obviously. All 100, the quantum walk approach does better. So this shows something that may not be surprising from these energetic arguments, because you don't have those where you do things sequentially. This is showing that you're really getting an advantage from the analog approach, even when you discount the fact that you're sweeping, and doing a sweep is removing energy. Even if you really just do a static fixed Hamiltonian, that's still better than doing one Trotter slice than another Trotter slice. We can then zoom in, look at a single instance. These are just random spin glass instances. These are actually taken from, there was a paper where it published a repository of these for reproducibility. It was on a couple slides ago. It's also referenced in the paper. And what you see here is for the quantum walk-like protocol, your success probability versus time is, as long as you make your gamma, which is your level of fluctuation, so your ratio of your driver to your problem Hamiltonian, as long as you put that in the right range, your probability goes up and down, but it can get pretty high. Of course, in reality, you don't know where these peaks would be, so you just have to kind of pick a time randomly, but you still do pretty well. On the other hand, with the QAOA, it only works, so this beta is how much you turn on your problem Hamiltonian. It only works if you have that on for a relatively short time. This makes sense, because if you have that on for a long time, if your phase wraps completely around, all of a sudden going to a much higher energy state actually looks like going to a lower energy state from the perspective of the system. Your phase interference will happen the same way, and so you get, some, I would say, sort of accidental places where your success probability goes up, but overall you only get these like single peaks at the beginning, and they're much shorter. We've made the color axis overall on the same scale. So indeed, this is showing that the analog approach really gives you major advantages compared to this digitized approach, even when you discount the fact that you're really doing a time-dependent Hamiltonian. An advantage is still there, and this kind of goes back to these energy conservation arguments. Now we can think of doing 5 stages, so either doing QAOA, where you do problem driver, 5 series of those, or where you do a quantum walk in multiple stages, where you turn one on, turn the other one on, or you turn the system on with one gamma, reduce the gamma, do it with a different gamma, et cetera, et cetera. where gamma is the ratio of the driver to the problem Hamiltonian. There's a little bit of tricks on how we parameterize this, so we could parameterize the two in the same way. You'll just have to believe me that we did something that makes sense. You can see it all in the paper though. We did end up doing something that makes sense, but we wanted to define them both with the same parameters as gamma and this delta gamma. So the gamma is the ratio of driver to the problem. The delta gamma is how much you change in each step. There's details on how to get the math right that I'm not going to go through, but we did it in a sensible way. So if we look at the results, gamma versus delta gamma, on the right, we have quantum walk. On the left, we have the QAOA protocol. And again, we see the same kind of result. And this is again for a single spin glass instance. We see high success probability, much higher success probability than quantum walk. We can get up to around 80%, whereas we only get around 50% for the QAOA protocol. Another more subtle thing is my peak is at a much higher value of delta gamma for the simultaneous protocol. So what I would argue there is that there we're able to take much more advantage of the fact that we're sweeping the values. Whereas for the digitized version, we're not really. And yeah, this basically, the way I said it here is that successive quantum walks can do a protocol that more faithfully reproduces annealing. Now people have obviously looked at things like Trotter errors before. The previous talk looked at this, but a lot of that work I think has been in the perspective of trying to do a simulation. Here we don't really care if we're successfully simulating the system dynamics. We're treating it as an optimizer. We want to know, do we find the answer? And the answer is you find the answer better in the analog setting. And this is consistent with the energetic arguments that we've made before. So now I'm going to move on to the next sort of section of the talk, which is hardware-aware encoding. The idea here is to develop and apply techniques of stating a problem in a way that's conducive to being run on a physical analog solver. So if we're thinking of flux qubit annealers, which is where the experiments I'll show were carried out, with flux qubit annealers, in fact, these considerations or qubits are really at a premium. Connectivity really matters. The encoding can affect the dynamics. In the end, this is a system that's undergoing physical dynamics, and it's worth thinking about it. And there are temperature and precision limitations. And really the idea of what I'm calling hardware-aware encoding versus just traditional problem encoding is you might consider techniques that might not be worthwhile on traditional solvers. You might consider techniques that actually might be detrimental to performance on a more traditional solver. But you really start thinking about how this works. I'm just going to point out that in general, this probably isn't actually an annealing specific thing. People just haven't thought about this as much with gate model machines because their machines aren't there yet. They're not mature enough to be at the point where thinking about this makes sense. So one example of this is domain wall encoding. I'm very excited to hear the next talk, which is someone doing some experiments on this. But basically, if you have higher than binary discrete variables, you can define a 2-index object that basically takes value 1 if the variable takes value A and 0 otherwise. And then we can make a discrete model of pairwise interactions between these terms. And we can take this and we can build up a model on encoding. I'm not going to go through the details of how domain wall encoding works. It's in this paper. But basically what you're doing is you're encoding onto a spin chain and you put frustration on it so that the position of a domain wall maps to the value that it takes. Now the key trick here is that you can map arbitrary interactions between the variables to this domain wall encoding. And an interaction and those interactions are quadratic. You don't need overhead to make higher order terms, otherwise it would kind of be a no-go. One hot is the traditional way to do this, where you constrain a bunch of variables, so only one of them can be 1 and the rest have to be 0. So there's now some fairly old results. You can get improved performance on max 3 coloring on D-Wave devices. In fact, the encoding in this case made a bigger difference than using the newer device. Yeah, this is where trying to have discrete problems to encode. You can make arguments about not only, so it's domain wall encoding, if you go through the math, you use 1 fewer qubit per variable, which doesn't sound like much, but if you're doing a 3-color problem, that reduces your number of qubits by 2/3, because you use 2 qubits per node you want to color instead of 3. But beyond that, if you think of doing a transverse field update, if you have a spin chain and you're moving a domain wall, you're moving a point where it goes from 0 to 1 down the chain, that can be accomplished by a single spin flip. Whereas if you're doing 1 hot encoding, you have to enter an invalid state if you're doing single spin flips and then go back out. It has to be done perturbatively. And so what I'm going to talk about here is a specific experiment where we actually compared domain wall and 1 hot encoding. What we did here wasn't actually a real hard problem. We just took the constraint structure you'd have from a traveling salesperson problem, and we were just looking for valid solution. We didn't actually put any path distances in it, but it was convenient for the experiment we were doing because we could easily obtain thermal samples. And we can measure the freeze point and the effective temperature. The details of this, I'm not going to go through here, but basically what we did is we fit the distribution to a thermal distribution. We know the schedule of the device. From that, we can back calculate when is it frozen, of what value of S is it frozen. And so here's the values. We can see for 1 hot, you're effectively at a higher temperature, which means you're freezing earlier in the init. And there's all kinds of details to get this calculation right. You have to consider the embedding strength. Here, the embedding strength we ended up using, just using the default protocol, was actually slightly worse for domain wall, but it still came out ahead because of this later freezing. So now that we have these encodings, we're moving on to actually using them. And actually thinking about cases where you might apply these to real problems. So the first example I'm going to talk about is a project I've been doing at Newcastle with Unisys, which is looking at loading cargo onto an airplane. It's highly connected. It won't have the same structure that coloring problems have. So some of the very good performance on coloring problems that you see on the domain wall, you won't necessarily see here. And the idea here is to use this problem as a test. It should be a test, not text case, for advanced methods. We also, Mano's actually with the INQA. And yeah, you can go to his poster, but what are the results? Well, we did a number of tricks here, actually, not just domain wall. We did advanced embedding tricks. We looked at the problem size and the average embedding size. And what we can see is if we use domain wall and a few other tricks, one of these tricks is just to use methods that use fewer slack variables, because the formulation that Unisys gave us, they're running on classical optimizers. They don't really care how many slack variables they have. They have lots. We thought of ways that you could easily get rid of some slack variables. You end up having maybe 2/3 as many qubits after you've embedded. So that's pretty significant. We're running experiments. There's also some tricks we use to improve embedding efficiency. I can't talk about all the details there, but an additional advantage is not only did they make the embedding more efficient, they made it much faster to do, much faster than linear embedded. So Another project we've looked at using actually a different hardware-aware encoding trick. This is my student Payet. He also has a poster number 4, is to look at if you have a quadratic constraint, which requires everything to be fully connected, which is going to make embedding very hard. What if you instead replace it with a linear constraint? And we have experiments in theory and numerics on this. A lot of work went into this. I am going to note that this is very similar to a strategy that Ozeki looked at in an earlier paper, which is looking at a similar idea. And what we see is if we make the constraints linear, if we choose the right value, which we do quite a lot of work at looking at how to do that. I don't have time to talk about it here. We have a higher chance of being feasible. So the orange is the quadratic penalty method, the blue is the linear penalty method, and we're much closer to optimal. So this R here is approximation ratio that gets very close to 1, which means we've basically succeeded. And we get much more compact embeddings. I really like this figure down here. Basically, we're trying to embed the graph in A. But if we have a quadratic constraint, everything becomes fully connected, and we end up with the embedding in C, which is a mess and takes up a significant chunk of the chip. If we do the linear method, we get a much smaller embedding. Of course, you have to be careful about how you choose these parameters. Payet can explain more of this in this poster, or you can look at his or you can look at the papers, which actually the first of the paper was recently accepted in New Journal of Physics, which is exciting. I give the archive number here, but it's also in NJP. So now shifting gears again, the slide logo has changed a bit because this is consulting work I did with QCI, and I'm actually going to talk about some of what quantum computing, the company that I work with a fair bit, does here, about exploring different paradigms. So transverse field annealing is a fantastic paradigm, and I tell everyone else here. But we've got to thinking, well, what else is out there? Are there other things that are worth doing? And we found some interesting results. One thing we started to think about theoretically is that, okay, adiabatic theorems represent one kind of Zeno effect. There are other kinds of Zeno effects based on measurement and things like that. How can those be used in computation? Basically, the idea there, is you have amplitudes that have to build up, and adiabatic quantum computing is one way to, you reverse the phase on an excited state, and that prevents amplitude from leaving the ground state and going to the excited state. If you work out the math, though, you can do the same thing just by removing the amplitude from the excited state before it builds up, or by actually just removing the coherence. So what about equivalent protocols? And people have looked at this a little bit, but not very systematically. So myself, Jesse Bearwald, and Ralph Dreedy went to look at, well, theoretically, can you get a Rover type speed up with other kinds of Zeno effects? And the answer, perhaps unsurprisingly, is for dephasing, or for states where you remove amplitude from the excited state. You actually can, we looked at 9 settings, you actually can get an optimal advantage. There's this paper where we talk about it. There's a whole lot of details I'm not going to go into here. But you can do that both in a continuous version, where you really have a master equation, or doing it in discrete operations. And in all 9 settings, you get the optimal square root n speed up for a Grover type problem. This is, something people have looked at a bit before, but not very systematic. And so we really systematically looked at it. So then we got to thinking, well, that's great, but can you solve more practical problems using, say, a Zeno effect based on losing amplitude, based on losing probability to be an excited state? So if you think about this, you can't use a qubit as your basis unit. If you take a qubit and you couple loss to one of the states, you're only left with one state that's trivial. You can't do computation with that. You need a 3-state system. And so then what we can do is we can think of, you have a 0, 1, and undefined state, and then you can define a state that's some combination of those that you sweep, that you couple dissipatively to, and you can again say, well, what I want to do is couple to that in some way, using, I could do it by giving that state a higher energy, do it adiabatically. I could couple loss to that. I could couple, do decoherence. I'm not going to go through too much of this paper, but a key finding here is a mechanism based just on loss or decoherence. It works, but it actually doesn't work very well. You need very long run times to get a high success probability. Part of it is you can't implement the frustration that you can in an adiabatic setting. A very interesting side result that I'm going to highlight to this audience is we actually looked at this 3-state system and said, well, what if we just do things adiabatically? And if you do it in the right way, again, I don't have time to go through the details of how all these work. You can actually imagine if you then include constraints and you make the constraints very strong. In a normal transverse field setting, if you make your constraints too strong, they stop the dynamics. At least if you have constraints where your manifold of states you want to go to are disconnected, so like K-hot constraints, versus, these are actually satisfiability constraints, but similar idea, versus in this 3-state system, because you can pass through this undefined state, you can actually make your constraint strength arbitrarily strong, and your success probability instead sort of asymptotes to a value. So you can have a non-perturbative way of implementing constraints. This actually looks a lot like, for people who are familiar with atomic systems, you can implement this in a way that actually looks a lot like Stirrat, which is a standard state preparation protocol. Again, the details are all in this paper. So now I'm going to talk just a very little bit, because I have very little time, about QCI in general. So here's some sort of theory we did, myself, Jesse, and Rose did to support some of the efforts on the hardware. There's a vision here to build a bit of optical hardware. This is what people eventually want to do, is to build a machine. Our hardware team wants to build something that's like a coherentizing machine, but uses has controllable loss and controllable gain using an effect called xenoblockade, and basically both controllable loss and gain, and fully optical setting, what we eventually want to do. So you can now see why results showing you need both loss and gain fits in with what the company's looking at. Of course, what we have today is not quite that yet. Right now, the hardware is based on FPGA feedback, because implementing this sort of mixer is hard. Implementing that all optically is difficult, but everything's continuously improving, and the company's building has built a foundry in Arizona to make things out of lithium niobate. There's a paper which gives some early experiments on this and shows a max cut example. The interesting thing about this is this has more flexible kinds of encoding. It's similar to a coherentizing machine, but we use an amplitude encoding. So you can do continuous binary, integer, and interactions that are beyond quadratic. So a lot of these good things that test drivers said you might want. And now I'm just kind of gonna shamelessly plug some of the contacts for QCI. If you have questions about the hardware, I can't really answer them. I would recommend contacting people there. I'm also going to highlight something that I actually worked quite a lot on, and was actually a lot of fun to work on, which is the resource library, which has tutorials on the hardware, but also has lessons on a lot of the related concepts. that were actually really fun to write. I was involved in writing a lot of these, the UX designer. They're also posted on Medium. So I think that's pretty much it. I think we have some time for questions. Sorry, a little bit into the question time.
If what represent question. Question. Okay, I will do fast. So the wondering how you can implement the first part of the presentation,
The first part,
quantum walk.
quantum walk.
Implementing the gate model.
So, the idea here is very similar to annealing. So if you have a driver and a Hamiltonian and a mixer Hamiltonian on at the same time, one thing you could imagine doing is you could imagine doing basically an anneal where you anneal very, very fast, so fast effectively nothing happens. Leave everything at a fixed sort of value of the annealing schedule, and then anneal very fast at the end and measure out. So that would be one way to implement a continuous time quantum walk.
You mean that can be implemented in the current DWeb system?
I don't believe it could, because doing very, very fast flinches is actually difficult on superconducting devices.
It's
So
quickly you need.
yeah, because what you need, so the staying in a fixed value isn't hard, but the changing values very quickly in a superconducting system. And I mean, they would make phenomenal progress on being able to do this, but I don't believe it's possible to do it effectively instantly. Now I do think in like cold atom platforms, you don't have the same limitations. There you potentially could really do a quantum walk. I think while doing the quantum walks is interesting for theory and for understanding theoretically what's going on in annealing, you actually, in terms of solving problems, you're probably actually better off doing annealing. One of the results we found in this Kellison paper down here is that actually doing the sweep pulls energy out quite effectively. So you actually want to change the values. So more we're using the quantum walk as a theoretical tool. It would be cool if you could implement it on real hardware. But I think it doesn't necessarily give you any advantage in optimization. We actually were doing a quantum walk rather than anneal to try to take away advantages from the analog one to make a fair comparison, not to try to give it as many advantages as possible.
Okay, thank you. Any other questions, comments?
There was a lot of material, and I think I didn't completely understand when you were talking about the benefit of the Xeno approach kind of towards the end of the talk.
Yeah.
So you brought up this old paper, which I have read, but then I think I didn't completely understand the newer work and what the takeaway was. So did you find that through like a measurement-based Xeno effect, you could do better than just through coherent evolution, or what is the?
Well,
what is the?
So are you talking about this paper?
Right.
Yeah. So is this the one you're asking about? This newer archive one?
Yeah, I was just wondering if you could say a little bit more about,
okay.
about what you found.
Yeah. Of course, I'm happy to. So what we looked at, what we found was you have these sort of three-state systems, because you have to do that to use it for computation. What we found is if we looked at satisfiability problems, So those are sort of nice problems to look at in this way because they only, they only have constraints. You don't have to worry about also implementing an objective. What we looked at, and we did look at measurement-based effects, but we looked at other ones too. Is we looked at, for example, if you measure whether it satisfies a constraint and you measure whether it's in the state manifold, this state manifold, and you slowly rotate the manifold and do the measurements, you will eventually get a satisfying distribution, but the rate at which your probability approaches 1 is very slow. And the reason that we attribute to this is that if you look at the imaginary eigenvalues if you're looking at this with a Hamiltonian, with an imaginary Hamiltonian with digitation, if you look at the eigenvalues, what happens is they're degenerate at the beginning. You have these extra degenerate states. And so you have to go very, very slow at the beginning. And that's kind of why I'm saying it works technically, but not very well. So that was the result we found. If you do the adiabatic version, without doing anything special, you get the same thing. It technically works, but not very well. But adiabatically, you can have frustrated terms. You can add an extra term that penalizes being in this undefined state. Once you do that, you suddenly have a gap at the beginning and everything just works much better. So a lot of this was exploring what you could do with different kinds of Zeno effects. Our main conclusion was probably doing something based on either just measurement, just decoherence, or just loss isn't a great idea. The thing that we didn't actually test, but we heavily suggested, was that doing something with both loss and gain is probably better.
Yeah, that's interesting.